Maxwell's equations are four equations which form the foundation of classical electromagnetism. They describe how electric and magnetic fields are generated by charges, currents, and changes of fields. They're named after the 19th century Scottish physicist and mathematician James Clerk Maxwell. I'm going to present these equations in an easily understandable form. Anybody who has knowledge of physics, the British A-level, should easily be able to understand them. The equations can be written in two forms. The integral form is used for computing the fields over an entire region of space, whereas the differential form tells you the fields at a single location. Let's have a bit of background before we go on to the equations themselves. Most of you will recall Coulomb's law. The force between two charges follows an inverse square law and is repulsive if the charges have the same sign. The constant epsilon naught is the permittivity of the vacuum. In any medium, such as air, we need to replace epsilon naught with the value epsilon for that medium. If the two charges have different sign, then the force is attractive. We can rewrite the equation of Coulomb's law as F equals Q times E, where E is Q over 4 pi epsilon naught r squared. E is called the electric field. The electric field is defined as the force per unit charge acting on a small test charge. The units are newtons per coulomb, force per charge, or equivalently volts per meter. The electric field is what we call a vector field. This means it has a direction as well as a magnitude. So at a given point in space, it has three components: Ex, Ey, and Ez in the X, Y, and Z direction. In this video, I'm going to use the notation where any quantities in bold are vectors. Quantities not in bold are scalars, so they have a magnitude only. The letter E, not in bold, signifies the magnitude of the electric field. The total electric field at any point in space is calculated by summing up the individual electric fields, which might be due to, for example, charges located at different points in space. For example, the electric field E at the location marked by the black dot is given by summing up the individual fields caused by charges Q1, Q2, and Q3. Now, before we talk about magnetic fields, we need to say a little bit about multiplying vectors. The first way of multiplying vectors is called the scalar product, sometimes the dot product, and the product of two vectors multiplied this way isn't a vector, it's a number, and the magnitude of this number is equal to the length of the two vectors multiplied together times the cosine of the angle between them. And the formula for working this out is below. The vector product of two vectors is written as A cross B and is a vector which is perpendicular to both A and B, and the magnitude of this vector is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. And this is the formula for working out the vector product. The force due to a magnetic field acting on a charge moving at velocity v is given by the vector product of the magnetic field and the direction, the velocity the charge is moving in. And because it's a vector product, its direction is perpendicular to both v and b, which means that if the charge is moving parallel to the field, either directly in the field's direction or directly opposite, then the magnetic force is actually zero. The magnetic field strength is defined as the force exerted per unit charge moving at a unit velocity perpendicular to the field direction, and the units would be newtons per coulomb per meter per second, but this is more commonly known as Tesla. Okay, we can now go on to Maxwell's equations. Okay, well, let's look at Maxwell's first equation in integral form. It tells the electric flux out of any closed surface is proportional to the electric charge enclosed by the surface, irrespective of how that charge is distributed. Electric flux is a scalar quantity and is the amount of field passing through a surface. So if we look at a surface with area S and a field of E, then the electric flux is equal to the magnitude of E times the area times the cosine of the angle between them. And we can actually write this, interestingly, as the scalar product of E with a vector S, where S is a vector which has direction 90 degrees to the surface and magnitude the area of the surface. But we can generalize this to a surface which isn't even and a field that isn't even. If we take a very small element, then the flux passing through that small element is still equal to the vector product of the field passing through and ds, where ds is a tiny vector which is at 90 degrees to this tiny piece of surface. If we integrate over the entire surface, then that will give us the flux passing through the surface. So if we look at the integral over the closed surface a whole, what this is telling us is the flux which passes out through this closed surface is equal to the charge enclosed divided by the constant epsilon naught, which we've met before. So from Maxwell's first equation, the amount of flux coming out of these surfaces is the same. It doesn't matter with the size or shape of the surface, and it doesn't matter where the charges are situated within the surface. Providing the charge enclosed is the same, the flux coming out is the same. Now, to go on to the differential form of Maxwell's equations, we need to understand a bit about divergence and something called Gauss's theorem, which I'll talk about next. The divergence of a vector field is the limit of the amount of flux coming out of a closed surface divided by the volume enclosed by this surface as the volume shrinks to zero. If the divergence is positive, then flux comes out of this point and it's a source of the vector field. If the divergence is negative, then we say it's a sink. The vector field goes into the point. And if it's zero, then it's neither a source nor a sink. As much vector field flows in as comes out. Mathematically, it can be shown that the divergence of a vector field is equal to the sum of the partial derivatives at that particular point. So if we take an example, a simple vector field where the x component is x, the y component is y, and the z component is z. So what we'd see with this vector field is the further away we go from the origin, the stronger the vector field is. It moves away from the origin. In fact, it diverges from every point. The divergence of that vector field is simply derivative of x with respect to x is 1, derivative of y with respect to y is 1, derivative of z with respect to z is 1, so the divergence is 3, which is positive everywhere. Okay, now that we've covered what divergence is, we can talk about Gauss's theorem. This states that the surface integral of a vector field over a closed surface, the flux through the surface, is equal to the volume integral of the divergence over a region bounded by the surface. In other words, the net flux out of a region is the sum of the individual fluxes of the sources within the region. Okay, let's get to the differential form of Maxwell's first equation. Starting with the integral form, we can switch the right-hand side to be the volume integral of the divergence using Gauss's theorem, which we've just discussed. Now, if we consider the volume as a whole, the charge density at a very small region, we're going to call this rho. And if we integrate over the entire region, rho, so we integrate rho over the entire region, then it gives us the total charge enclosed in the volume is the volume integral of rho. So we can substitute the right-hand side with the volume integral of rho. Now, if the right-hand side and left-hand side are equal for any volume v, regardless of its size or shape, then we can drop the integral sign. And we have then Maxwell's first equation in differential form, which is the divergence of the electric field is equal to the charge density divided by epsilon naught. So Maxwell's first law in differential form tells us if the divergence is positive, we have a positive charge density at this point in space. We have a source of the electric field. If the divergence is negative, then we have a sink of the electric field. And if the divergence of the electric field is zero, there's zero charge density at this point in space, and it's neither a source nor a sink of the electric field. Okay, let's go on to Maxwell's second equation. This tells us that magnetic flux out of any closed surface is zero. Magnetic flux is a scalar quantity and is the amount of magnetic field passing through a surface. The SI units are Tesla, meter squared, or Webers. We're taking a simple example, a flat surface having area S, where it's angled at theta to a uniform magnetic field. The flux passing through S is simply this magnitude of the field times the area times the cosine of the angle between them. For the net flux to be zero for any closed surface, the total magnetic flux in must be equal to the total magnetic flux out. In differential form, Maxwell's second equation tells us the divergence of a magnetic field is always zero. There are no sources or sinks, where at each point in space there is zero magnetic charge. This even includes the area around the poles of a permanent magnet. Maxwell's second equation tells that magnetic monopoles do not exist. Okay, let's go on to Maxwell's third equation. The EMF around a closed loop is equal to the negative of the rate of change of the magnetic flux within the loop. It describes how a magnetic field will interact with a closed loop, in other words, an electric circuit, to produce an EMF, a phenomenon known as electromagnetic induction. It's the fundamental operating principle behind transformers, inductors, many types of electric motors, generators and solenoids. And it's also probably more commonly known as Faraday's law of induction, after the English scientist Michael Faraday. Okay, let's look at the electric field drawn as the blue lines around a closed loop. You can see that the electric field isn't constant as we go around the loop. It can vary both in magnitude, which is the length of the line, and direction, which is where the line is pointing. Okay, let's focus on the left-hand side of the equation. If we're considering electric field E and a small element of the loop, L, then the change in EMF due to the electric field over this small element is due, where due is the scalar product of E and the small line element dl. If we then sum this up around the entire loop, then we end up with something called the induced EMF or voltage around the entire loop. This integrating around the entire loop is known as a line integral, and this value is measured in volts. Okay, well let's look at the right hand side. The integral on the right hand side is this total magnetic flux through the closed loop L. S is the surface enclosed by this closed loop. So what this also tells us, because the induced EMF is equal to the negative of the rate of change of the total magnetic flux, if the magnetic flux isn't changing, it's fixed, there is no induced EMF. However, even if we have a static magnetic field, if the loop itself is moving, then the total flux passing through the loop will change constantly, and so there will be an induced EMF around the loop. To get to the differential form of this equation, we need to understand something called the curl of a vector field and also Stokes' theorem, and that's what I'll talk about next. So the idea of curl is to do with rotating vector fields such as this one. So the orientation of a vector field rotates in space. If we have a rotating vector field, we can define the curl of the vector field at a particular point, which is normally written del cross f, as a vector, and its magnitude is the amount by which the vector field rotates around that point, and its direction indicates the direction of the rotation. So because the curl is a vector, it has components in the x, y and z direction. Let's just look at the component of the curl in the y direction. It's equal to the limit of a line integral around a closed loop, which we'll call Ly, divided by the area enclosed by this loop. And Ly is perpendicular to the y direction. And you can calculate the component of the curl in the x and z direction in a similar way. In this diagram here, I've just shown how the component of the curl in the x direction is calculated. Mathematically, you can express the curl of a vector field at a point in terms of the partial derivatives with respect to x, y and z as shown here. Now we've covered curl, I'll briefly go through Stokes' theorem. This states that the line integral of a vector field over a loop is equal to the flux of its curl through the enclosed surface. So mathematically, this is how it's expressed. So if you can see, what we do is the total rotation of a vector field summed along a loop, the line integral, is equal to the total curl of the vector field within the area enclosed by the loop. Intuitively, the rotation of the vector field inside the loop cancels out when we do the integration by summation, and only the rotation of the vector field along the edge remains. Now we've covered curl and Stokes' theorem, we can go back to the differential form of the third equation. Okay, well let's get to the differential form of Maxwell's third equation. So if we start with the integral form, which we've seen before, we can replace the left-hand side with the integral of the curl within the surface. What we can do now is we can move the derivative of the magnetic field inside the integral sign. And then if we notice that the right and left hand integrals must be true for any surface regardless of its size or shape, then the right and left hand side must be equal. So what Maxwell's third equation in differential form tells us is a changing magnetic field causes a rotating electric field and vice versa. Okay, let's go to Maxwell's fourth equation then. In English, Maxwell's fourth equation says the line integral of the magnetic field induced around any closed loop is proportional to the electric current flowing through the loop plus something called the displacement current, which itself is proportional to the rate of change of electric flux through the enclosed surface. Now you'll notice in this equation there are two constants, mu naught and epsilon naught. Epsilon naught we've met before, the permittivity of free space. Mu naught is the magnetic permeability of a vacuum. In any medium we would need to replace both epsilon naught and mu naught with the values for that medium, but for the purposes of this talk we're just assuming it's in a vacuum. This is illustrated here. The first part of the magnetic field is caused by the current flowing through the loop, and it's the total current here, so it's the sum of the individual currents flowing in either direction. The second part of the displacement current is due to the rate of change of electric flux, and this again, if the rate of change is 0, then the second part is 0. Okay, let's get to the differential form of the fourth equation. If we start with the integral form, then we can replace the left-hand side with the surface integral of the curl of the vector field by using Stokes' theorem. If we then look at the current, then if we introduce the current density, which is a vector, which is the current flowing per unit area in a given direction, so the total current I flowing through the surface is just the surface integral of J over the entire surface. So then we can replace the term mu naught I with the surface integral of J ds times mu. The next step is to move the differential of the electric field inside the integral sign. So what this tells us once again is if the right and left hand integrals must be equal for any surface, then the right and left functions must be equal. So to put it another way, the curl of the induced magnetic field is equal to mu naught times the current density plus mu naught epsilon naught times the rate of change of the electric field. So the curl of an induced magnetic field at a point in space can be caused in two ways, by an electric current density and by a changing electric field. Well, thank you very much for watching. I hope you know a little bit more about Maxwell's equation and the video has been helpful. One thing that came out of equations 3 and 4 is the possibility of electromagnetic radiation, which a changing electric field continually gives rise to a changing magnetic field and vice versa. Thank you very much for watching.